Alright, so here we are again, and this is section 2 of chapter 5. It's not horribly new information compared to what we were doing in section 1, and so you'll tend to see me go through this a little quick. But let's say we have some random variable that's normally distributed. So something about what we've measured is randomly distributed, and we have a mu, or a mean, sorry, instead of saying the Greek, of 500. And it has a standard deviation of 100, whatever we measured. And we want to know what the probability of grabbing some variable less than 600 in it, some random variable. And so for probabilities, what we want to be able to do is go from x to z. And so our kind of thing that we do is we see our x, we transfer it into a z, and we transfer our z into a probability. And that probability is the same as the probability of that z score or the x value. And so the z score is our translation unit, so we take x minus mu over sigma. Or in this case, we have, what is our x score? 500. No, our x is 600, my apologies, right? Because that's the upper level. There it is, 600. Minus the 500 divided by 100, or that's going to be equal to 100 over 100, or 1. And so we want the probability that z equals 1. Well, we can go look that up in our table, and we get that, what is the probability of 1? Let me jump over to a table here. Let's see if I can get the table together for us here. Pearson, there we go. So it's a positive 1. Let me make sure you can see the table. So I come here, go to table, and let's see, we go down to 1.0 and over to 0, and 1.0 is 0.8413. 0.8413. 0.8413. And so this probability is 0.8413. And so we can say the probability of getting a value from our distribution less than 600 is 84.13%, or the probability is 0.8413. That is equivalent of the z-score of 1. And so with this as our translation tool, we can translate from what we measured to the standard normal. And the standard normal will give us the probabilities that we need. Alright, so let's do one more here. Yeah, this is the one I like, shoppers in a store. And so this is on the slides. It's example 2. And it says that a survey is done, and it indicates for each trip to a supermarket, a shopper spends an average of 43 minutes. So 43 minutes is the average in the store, with a standard deviation of 12 minutes. And we're saying that this is normally distributed. And so what we want to find out is, hey, if 200 shoppers enter the store, what is the probability, or not, what is the probability? How many spend between 22 and 52 minutes in the store? And this might be good, like if you're an advertiser and you're like paying for something on the loop in the sound system at the store, and you want to figure out, you know, how often do you have to play your advert to be heard by a certain amount of shoppers, right? That's also how they determine ad revenue. And so we have a probability of our x value being between 22 and 52 is what we want to find. So for that to work, we need to convert these x's to z's. And so our z of our lower score is going to be 22 minus the mean, right? Because our z is the x value minus the mean, divided by 12. What is that here? Come over here really quick and play off the calculator here. So what did I have for those? I had, oops, it's clear. Always do my fractions. 22 minus 43 divided by 12. So negative 1.75. So let's come back over here. And that's negative 1.75. So let's do that. Negative 1.75. And then Z2 is 52 minus 43 over 12. And we'll come back to the calculator again. Whoops, get to the calculator. There's the calculator. And so upstairs was 52 minus 43 divided by 12, and that's 0.75. So let's put that down here, 0.75. And so this translates into the probability of a z-score of negative 1.75 for the lower end and 0.75 for the upper. Now at this point, I'm going to say, hey, there's two ways we can do this. We can, do the subtraction or use the tables, or use the tables, or we can use the calculator. Since people here have both, or people I'm talking to might have one or the other, I'm going to do it both ways for this one. And then in the future, I'm going to say use the way you've been doing it. So the probability of this is equal to the probability of z less than 0.75 minus the probability of z less than negative 1.75. So if I look up 0.75 in my table, so 0.75, 0.7, and there's the 5, 7734. So 7734. 0.7734 minus, and now I'm going to look up the larger, or the lower end probability, negative 1.75. So I have to come to my negative table. Hit the button again. There we go. And so negative 1.75. And so that's 0.0401. Whoops, that was me. You don't want to see me. 0.0401. And you subtract those and we get 333.73. So this says the probability of being in between those two things is 0.733. That doesn't tell us how many things there are. So if we have 200 people, if we multiply them by the 0.7333, then we end up getting 146.66, or approximately 147 people. So remember, this thing asked us for people. And so about 147 shoppers would be here. All right, if I were doing this on my technology, so I'm going to flip over to the calculator here. I want to do this all in one place. And so I'm going to say, you know what? I'm going to have 200, that's the number of shoppers, times the probability that comes out of a normal distribution. So there's, the normal CDF. Now my lower was 22 minutes. My upper was 52 minutes. My mean was 43 minutes. And my standard deviation was 12 minutes. That was everything in the problem. And I get the 146.66. So notice how the technology does the Z translation for us. Please be comfortable doing the Z-score. You need to double check your technology, and this will help you double check things. I will ask you about Z-scores on their own. All right. That really is all of section 2. If you look at the slides in the book, they go rather quickly. What we're doing is we're using the fact, hey, those Z-scores are the translation from what I measured into probabilities. And we put it all together in the terms of the problem. And what we're going to do next is we're going to start with a probability and pull back x values from it. Because anything we do mathematically should be reversible.